Okay, today we're going to do an application of charged plates, and we're going to talk about this later on in later units, but it applies well to this part of the course now too. So we're going to talk about it now, and then we'll come back to it again later on with more details. But what happened in 1909, Robert Millikan, he came up with an experiment. His goal was to try to figure out what the charge of an electron is, and he actually found out quite a bit of information from his famous experiment. So what he did basically was he took charged plates, so he had two charged plates, and he drilled a hole in the top one, and then what he did was he sprayed fine drops of oil. So he had like a kind of like a perfume bottle type sprayer, and basically what he would do is he would spray oil in. And what he thought of is he said, well, we can charge these oil droplets, so just by friction and so on, he would get the droplets to gain a negative charge. So then what he did was he thought, well, if I can get these droplets to fall between the plates, I can actually create an electric field and a gravitational field. So he just sort of sprayed a mist of droplets around the top plate, and then some of them, by chance, would fall through the hole. Okay, so then he'd get this electric negative charged oil droplet in between the positive and negative plates. So what he did then was he looked at, if we had this negative plate and we got this negative on the bottom, positive on the top, we got this negatively charged oil droplet, we would know that gravity would pull them to the bottom. But if they were negatively charged, then it would repel upwards. So then gravity is pulling it down, but the electric force is pushing it up. So then his logic was, well, these two things actually should balance out. So our oil droplet should have gravity going one way and electric force going the other way. So if those two forces balance, then the oil droplet would float. And that's exactly what Millikan did. So he just sprayed them randomly, and anytime he got a negative droplet to go inside the hole, he would adjust the voltage to try to see if he could get it to float. So because those two are equal, really all we're doing is we're saying that our electric force equals gravity. We know with electric force we have Q times electric field. Gravity is mass times gravity. And we can change electric field to voltage over distance. And that's it. So basically what he tried to work with was mass times gravity times the distance between the plates divided by voltage. Okay, so you'd have these oil droplets, and the idea was, could he figure out the charge on the droplet just by rearranging these formulas? So he did, but the hard part was, how did he figure out the mass of the droplet? Right? With gravity we know, 9.81, the distance between the plates he could measure, the voltage he could change, so that was good, but the only problem was he didn't know how to measure the mass of the droplets. So he spent a lot of time to try to figure it out. So when these things would float, he looked through a little telescope, and what he did is he had etched lines. So if he saw that an oil droplet was the size of the lines, he could calculate then the radius and the diameter of the oil droplet. He could then figure out the volume, and he used the density of the mineral oil, and he could then calculate the mass. So it was a pretty complicated way to measure the mass of the oil droplet, but he got it to work. So from there, all he then had to do was use that Q formula to figure out the charge on the oil droplet. So mass that he'd measure, gravity times distance between the plates divided by voltage, and that would give him Q. One thing that was interesting is, as he did this experiment over and over again, every time he did it, depending on the size of the oil droplet and depending on the voltage, he found out that the charge was always some sort of multiple of 1.6 to the negative 19. So the smallest little oil droplet and the smallest voltage, he'd get 1.6 to the negative 19. If it was a bigger oil droplet and bigger voltage, something heavier, then he found maybe it was 2 electrons, so it would be 3.2 or 4 or 10 or 100 electrons, whatever. So during this process, he then figured out the charge of the electron, and from that, once we knew the charge, he rearranged the formula and then solved it for mass. So Millikan's sort of the famous for coming up with the idea of 1.6 to the negative 19 as our basic charge, and then using the formula he calculated the mass of 9.11 as well. So it was just basically QV over Gravity times distance is how we got the mass of the electron. And the number he came up with is pretty close to what we use today. So let's do an example. It's a pretty basic example. So it says we got an oil droplet with a mass. We've got it floating. The question is saying how many oil droplets, or how many electrons are on this oil droplet. So we got electricity, force pushing it up, gravity pulling it down. So we'd have QE equal to mg. An electric field, remember, is voltage over distance. So the question is, what is our charge? So mgd over voltage. So all we have to do is plug everything in. So our mass times gravity times distance between the plates, so 0.095 centimeters, which is 0.0095, and divide that by our voltage of 340, we get a charge of 9.05 times 10 to the negative 19 coulombs. So that oil droplet then, the charge on the oil droplet is 9.05. We know that each electron has a charge of 1.6 to the negative 19. So all we have to do is divide those out, and we're done the question. So 9 divided by 1.6, we get an answer of 5.6 electrons. Doesn't make sense that part of an electron, so we just round it to the nearest one. So in this case, we would say 6 electron charge. So that oil droplet has 6 electrons on it to be able to float in that sort of charged plate situation. Okay, so they're pretty easy questions, and there's one on the review sheet that I gave you that talks about floating the oil droplet, and that's all you have to do is balance your electric force with gravity. And that's all for today.